Hello, my name is Franco Pellegrini and I'm happy to present my work done in collaboration with Giulio Biroli. We want to describe the dynamics of a single hidden layer neural network with m hidden nodes and a single output. We call Wi the weights from input to node I and Ai the outgoing weights, so that the overall output f has this form. Now for large M, we consider the mean field limit, and we can write the output as an integral over the distribution ρ of the parameters. This way, the evolution of each node just depends on the average output induced by the distribution. We specialize this to a binary classification task with a hinge loss that looks like this, with y equal to plus or minus 1 being the correct label. This function is linear, for example, misclassified or classified below threshold, but a flat zero otherwise, which leads to examples being effectively removed once they are classified beyond threshold. If we also take real nonlinearity, the equations of motion for node I look like this. Basically, we have an average over the examples of a function u that keeps track of the data that are still active, and a step function from the nonlinearity of each node I. If we consider the case where the data are taken from a spherical distribution with a hyperplane separating the two labels, this average can be computed exactly. More importantly, the integral does not actually depend on Wi, and instead it always points along the vector w star perpendicular to the separator plane. Now this means that the evolution for all Wi only takes place along this direction, so that we can explicitly write the trajectory of the weights in the w parallel A space, and these follow the hyperboles that you can see here. This in turn tells us how fast examples are classified, and we can then compute the time dependence, so that we can directly compare our parameters evolution with the real training. These are the lines and dots in this plot showing a good agreement. Also, as was done in other works, we can tune the loss function with the parameter alpha to interpolate between a rich learning and a lazy learning regime. And since the geometry and the trajectories are the same, we see that the only difference between the two cases lies in how much each node moves before the finite dataset is classified. This gives us a clear example of the difference in learning between the two regimes. Of course, this is all under strong assumptions, but we comment in the paper on how this could be relaxed, and how, for example, overfitting originates from finite size effects that we can estimate in our model. As a last remark, we also show how this behavior can qualitatively describe the early stages of evolution for more complex tasks, such as parity MNIST classification, as you can see in this graph, where the reference direction is the difference between the averages over the two classes. For more details, please see the paper and poster, and feel free to contact me for any question. Thank you for your attention.